welcome. Okay, let us begin to look at one of the fundamental relationships when we consider phases in equilibrium, especially when transitions between phases take place, and that is called the Clausius Clayperon equation. We are going to start doing this and let us see how far we get today. Let us consider our system as a pure substance. We will start with pure substances, that is good to understand the basis. Let us consider our system as a pure substance in two phases, say alpha and beta at equilibrium, and what I would like you to note is that we have not specified the nature of the phase. These alpha and beta could be any two phases, they could be liquid and vapor phase, liquid and solid phase, vapor and solid phase. That is what is given here. The following discussion, unless indicated otherwise, is applicable for any two phases. They could be vapor liquid, solid liquid, solid vapor. Since the phases are in equilibrium, at those conditions of temperature and pressure, which we will indicate by the superscript 1, we can certainly write from the condition of equilibrium, the first 5 equations, equations phi 1 to phi 5 and so on. Mu alpha at the conditions specified by the temperature and pressure, we will indicate that by 1, must equal mu beta, which is the chemical potential of the pure component in the other phase, in the beta phase. This is the chemical potential of the pure component in the alpha phase at certain conditions of temperature and pressure, must equal the chemical potential of the same component in the beta phase at the same conditions of temperature and pressure. This automatically comes from the condition of equilibrium. Let us call this equation 5.8. In the neighborhood of this point, which means a very small region around this point, mathematically speaking, where the equilibrium conditions can be considered to exist. It is a hypothetical situation here, but we need the concept of neighborhood to completely develop this particular concept. Therefore, in the neighborhood of this point where the equilibrium conditions can still be considered to exist, we can write mu alpha 1 plus d mu alpha, that is a change from the point 1 in the neighborhood of point 1, equals mu beta 1 plus d mu beta. Of course, from 5.8, the previous equation, we know that mu alpha 1 equals mu beta 1, therefore, they can be cancelled, and therefore, d mu alpha equals d mu beta. The differential of mu alpha equals the differential of mu beta. Let us call that equation 5.9. Since the chemical potential of a pure substance is a function of only temperature and pressure, we can write equation 5.9 in terms of the expanded functionalities. This is the total differential, writing it in terms of partial differentials from the theorem in mathematics. D mu alpha is dou t of mu alpha at constant pressure dt plus dou p of mu alpha at constant temperature dp. This is d mu alpha. This equals dou t of mu beta at constant pressure dt plus dou p of mu beta at constant temperature dp. Let us call this equation 5.10. Now, let us take a slight detour to establish a few things, and then we will come back to our two phases and so on. From equation 2.15 that we saw earlier in the module number 2, dgt equals minus st dt plus vt dp. You recall this equation now. By now You must be familiar with this since we have seen this so many times and used it also. Plus of course this is a multi component system, therefore sum over all I mu I dni. This is the equation 215 that we saw earlier. Recall the reciprocity relationships that we again saw in the second module. Following the reciprocity relation, doing the reciprocity relationship for equation 215, the following relationships can be written out. Dou mu I dou p at constant t and ni equals dou v t dou ni. Now we are doing the reciprocity between these two. Dou mu I dou p at constant t ni equals, excuse me, dou v t dou ni at constant t p and all other n j's which are different from ni. We can write this, and that equals, this is nothing but the definition of the partial molar volume VIT hash. Let us call this equation 511, and if we do the reciprocity between this and this, we can write dou mu I dou t at constant p ni, dou mu I dou t at constant p and ni equals minus dou st dou ni at constant t p and all other n's which are different from this I, or all other nj's where j is not equal to I. And what is this? This is nothing but the partial molar entropy SIT hash. Hash is somewhat missing here, SIT hash. We will call this equation 512. Further, if equation 2.3, which can be written for the total values as Gt equals Ht minus Tst, this is the definition of Gibbs free energy, and we are writing this for the total values, not for a single mole. Gt equals Ht minus Tst. If this is differentiated with respect to Ni at constant T and P and all other Nj's, we can write in terms of partial molar properties as Git hash equals Hit hash minus Tsit hash. Now we are differentiating each term with respect to Ni at constant Tp and Nj, and by definition that derivative would be Git hash. By definition that this derivative would be Hit hash, and this one would be minus Tsit hash. We will call this equation 513, and from equation 216 we get Git hash equals mu I, the partial molar property with respect to the single mole there, therefore we get it equal to mu I. And therefore from equations 514 and 512, equation 513, from 514 and 512, 514 is this Git hash equals mu I, and 512 was this, which is the which we obtained from the reciprocity relationship. From these two equations we can write mu I equals Hit hash plus T dou mu I dou T at constant P Ni, which can be rearranged as, I am just rearranging this by T dou mu I dou T at constant P Ni minus mu I, and I am dividing this by T squared, is nothing but minus Hi, now I have taken this to the other side, minus Hi T hash by T squared, just a rearrangement. There is a reason for this rearrangement, or the reason for this rearrangement is this form is nothing but dou t of mu I by t p n I. If you are unable to see this, consider this as u by v, or numerator by denominator, denominator function into derivative of the numerator function minus the numerator function into derivative of the denominator function, which is 1 here, divided by the square of the denominator function, and that is the derivative dou mu I by t dou t at constant p n I equals minus h I t hash by t squared. We will call this equation 515. For a pure substance, the partial molar properties are nothing but the properties per mole of the pure substance, they kind of coalesce into each other, and thus the equivalent equations of 511, 512 and 515, when we write down the equations you can recall those, or you can go back and check what 511, 512 and 515 are. Dou mu by dou p at constant t equals v, equation 516, dou mu dou t at constant p equals minus s, equation 517, and dou mu by t dou t at constant p equals minus h by t squared, equation 518. Our 511 was when you had a I here and a VIT hash here, 512 was you had a I here and SIT hash here, and you had to take other ends also as constant, and here you had a I and HIT hash here and P and other ends to be constant here. Therefore, since these are written for a single mole of the pure substance, we can drop all these i's and hashes and so on, because the partial molar property becomes the property per mole of the pure substance. What we will do when we begin the next class is we will get back from this detour. We essentially wanted to come up with these relationships, and that is why we took a detour. When we begin the next class, we will get back to considering the two phases in equilibrium and the process of transfer from one phase or transition from one phase to another, which is the context of the Clausius Clayperon equation. See you in the next class.